Okay, we're going to do Bode plots, which is a tool for frequency analysis of control systems. This is an example of a Bode plot. It's kind of two plots in one, the magnitude or gain on top and the phase on the bottom, or the angle. The x-axis for both top and bottom is the same, and it's frequency in radians per second. This upper plot, the magnitude or gain, its y-axis is a log scale. But for the phase, the y-axis is just a linear scale. So they're both log scales along the x-axis. Gain is a log scale along the y-axis, and phase is a linear scale on the y-axis. This says about the same thing. So a frequency of 0 is minus infinity here. You can't put it on the scale. 1 radian per second is right here, 10 to the 0. That's 1 radian per second. This would be 10 radians per second. This would be 100 radians per second, right? And the gain, the log scale of gain, we call it dB for decibels. I think the next one, yeah, what actually gets plotted is 20. This is by convention. It's 20 the log, but when I say log, I mean base 10 log, the magnitude of whatever transfer function we're doing this. We're doing this for a transfer function. The Bode plot is the plot of the gain and phase of a given transfer function. We'll talk about what transfer function you might use later. So kind of get used to logs if you're not used to logs. Like the normal value of 100 is 2 in log. In dB that we use, it's 20 times that, so it'll be 40. So a gain of 100 is actually a gain of 40 dB. A gain of 10 would be 20 dB. Here's a couple other ones that kind of round off to numbers. 3 is about 10 dB, 2 is about 6 dB. Yeah, get ready for that. So what we're actually plotting is the gain of the transfer function in log. So it's going to be 20 times log 10 of the actual gain of this complex function here. And the phase, which will be the angle of the transfer function. And that's an inverse tangent function. Let's say you have an example. Let's say this is the transfer function we're getting. First thing we do is replace all the s's with j omega. I kind of went through this before, so I'm not going to go through why this occurs like this. First, replace s with j omega. Then I'm going to kind of normalize it to kind of get rid of these constants, so everything starts with the 1 as a constant. So I'll divide, say this term is going to be divided by 4. This will be divided by 2. This will be divided by 5. Anyway, you end up with this. And remember, you get the gain of the overall thing is the gains of the individual factors. Things in the numerator add. So in dB, the gain is going to be 20 times log 8 plus 20 times the log of this term minus 20 times the log of the magnitude of j omega minus 20 times the log of this guy, the magnitude of it, etc. Similarly for angles, they add and subtract. Angles in the numerator add, angles in the denominator subtract. So, excuse me, here's what you're actually would plot. This, and if you wanted to calculate that overall omegas, this is what you would calculate. And you would get some kind of curve like I showed you before. Same for the angles. For every omega, you calculate it and plot it, and you get some kind of plot. I already showed you. We're not going to do that. Well, we're aiming to plot Bode plots by hand. If you don't have to plot Bode plots, do Bode plots by hand, you can ignore this whole video. But we're getting to where we want to sketch a Bode plot by hand. So we're going to sort of approximate things first with straight lines called asymptotes. Let me kind of go through quickly why this kind of works. Let's go through things term by terms. You look at, there's 4 different kinds of terms. Constant term, a polar zero right at the origin, a real polar zero not at the origin, and complex poles or zeros. So the terms would look like this. How do you get the constant term? There you just go back to the original transfer function, plug in 0 for s's, and that's calculate the constant term. To put it in terms of dB, you have to take the log of this and multiply by 20. Poles are zeros at the origin. Gains is just this thing. So that ultimately is just the log of omega times 20. Plus, if it's in the numerator, minus in the denominator, and P is how big the power is. So that's linear. That's going to be linear in frequency on a log scale, right? And let's see. For the angle, it turns out to just be a multiple of 90, where the multiple is whatever the power is. So if those, let's say we go back to this, and those are the only terms in our transfer function. So our transfer function would look like this, just 8 over s, a constant over s. The gain is this, and the angle is just turns out to be minus 90, the constant. And look at this. When omega is 1 radian per second, log of 1 is 0, it's just this guy, which is in dB, the magnitude of this constant term. And then it's a straight line in terms of omega on a log scale. In fact, it's 20 dB per decade of omega. If that were the whole transfer function, here's what your Bode plot would look like. It's this straight line. It goes down 20 dB for every power of 10 in frequency. That's called 20 dB per decade. And it crosses this point, 10 to the 0, which is omega equals 1. It crosses that at that constant term. In this case, 20 log 8, which is about 18 dB. So that's where it crosses in a slope of minus 20. The angle was just a flat line of minus 90 degrees. What about the other terms? First, what about real terms? I'll try to go through this quickly to justify everything. You can calculate it. I'm not going to go through this in too much detail, but the gist of it is when this term here is small, when omega is much lower than that, constant that we divided by, then this kind of goes away, and this is just 1, that's 0 dB, and the angle of 1 is 0. So for small omega, omega is much less than that t, which we're going to start calling that break point. The break point for that term. Remember all the terms? Like here, the t was 4. Here, the t is 2. Here, it's 5. Those are the break points. For omega is much smaller than those break points, they don't contribute anything to the gain or the angle. Remember, they add. And then once the omega gets big enough, then what will it do? Well, add or subtract 20 dB per decade in gain. Well, for each power of this thing. So if this Q is 2, if that's a squared term, this would be 40 dB per decade. And the angle adds another multiple of 90 degrees. The idea is when we approximate it as straight lines, they're going to contribute, that term will contribute nothing for omegas less than t. And then once it hits t, the gain will be adding some multiple of 20 dB per decade, and the angle will be adding or subtracting some multiple of 90 degrees. Kind of summarizing all that, we're kind of running a little long here. But for the real terms, for the real poles and zeros, not at the origin, terms like this, they're going to add after you get past the breakpoint, and the breakpoint is this A. It adds nothing before the breakpoint, and after the breakpoint, it's a slope of 20 dB per decade in gain, and the phase will just add or subtract 90 degrees, a multiple of 90 degrees. Similarly, with complex terms, they're going to add a multiple of 40 dB per decade because it's like a squared term here, and the phase will be double 90 or 180 degrees. And the breakpoint is this omega n, which if your term looks like this, it's just the square root of this b. And if there's a power up here that's other than 1, it's just a multiple. So we'll get into actually step by step how to do a Bode plot by hand in a separate video. But that's kind of why it all works.